This podcast is supported by Siemens, your partner for industrial-grade AI.
Hi there, and welcome to a new episode of the Industrial AI Podcast. My name is Peter Seberg, and my guest today is Fabian Kreutmeier. He is specialist machine learning with HW Hydraulics. Hello, Fabian.
Hello, Peter.
Please tell our listeners who you are, where you're from, and what you do at HW.
Of course, yeah. As you already mentioned, my name is Fabian Kreutmeier, and I work as a specialist machine learning at HW Hydraulics. I'm now with HW since 2019 as a full-time employee, but I started in 2018 already as a working student. So it's now more than 4 years that I'm with HW. I have a background in electrical engineering, so I've studied electrical engineering at the Technical University in Munich, and throughout the specialization during my bachelor's and master's studies, I focused both on control theory and machine learning. And of course, also the combination of both fields, which we are talking about today.
Exactly. I was reading through, preparing myself a bit for today's discussion and really looking forward to. We had a discussion last week when I did a training course on data science for a German VDE organization of German engineers. So I'm really looking forward to exactly that combination of control theory and machine learning. Before we do that, tell us a little bit about the name of your company, says it, but still, in your words, what exactly does HW Hydraulics do?
Yeah, so as the name already indicates, we are a producer of hydraulic components. And I would say HW is a typical German Mittelstand. So it was founded over 70 years ago in Munich. We have now about 2,600 employees worldwide. And our headquarter is located in Aschheim, which is close to Munich. And there sits most of our administrative staff, including most of the R&D department where I am working. We don't have production in Munich, but the production sites are mostly located in Bavaria, at least the German production sites. They're in Kaufbeuren, in Freising, Barbing, and Sachsenkamm. Of course, we are also very international with subsidiaries all over the world, in Denmark, Italy, the United States, or China, just to name a few. And this comes also with quite a variety of customers since, hydraulics is used in very diverse applications. I think one of our biggest markets is the mobile machinery market with excavators, loader cranes, forklifts, and so on. So, all this heavy machinery that you see on construction sites. I think also very interesting areas are energy, for example, wind power, especially wind power. Also here you have a lot of hydraulics inside, and we have also customers in this area. And I think one thing that I want to mention, which is very interesting, we have since some years now a robot platform in our portfolio, the Rovo, which is made in Austria by HW Matro. And I think it's a very interesting addition to our product range, even it is not like an hydraulic component or an hydraulic machine. So it's more electrically.
Let's keep that one on the side maybe and talk about that later on as well.
Perhaps, yeah.
Very good. You mentioned German Mittelstand. Maybe we want to clarify Mittelstand as being small to medium size, and that what is typically very often the case when these kind of, and I would call you more like a hidden champion, I guess, kind of company, with 2,600 employees. Yeah, there's many different definitions of where the small to medium size stops and it becomes to be statistically, so to speak, a large company. But typically, I guess a hidden champion, those companies, those people that are in your market, and you just talked about what your market is, they know you as, as an important global organization, and maybe those that are not, maybe have not heard about you. Now, you mentioned customers, maybe a little bit of an application here. So when we talk hydraulic and we talk these mobile machines, I can imagine, but maybe you just want to say, what does that mean? We look into one of these big, you say excavators, for example. So where's your typical components in that application?
To drive such an excavator, you need the hydraulics to really get the power inside the machine. So you have the hydraulic cylinders. I mean, we are not producing the cylinders, but you control the cylinder through hydraulic valves. And here, for example, we produce the valves or the control blocks where the valves are located. Also, we provide, for example, hydraulic pumps and power packs to have a power source.
Right. Kind of what I could have imagined, but just also for our listeners. So moving one step further, because I assume that when later on, and maybe just let's dive in, we talk about, machine learning in your field, then one of your, if not the leading variable I could imagine, but you will tell us later, will be pressure, hydraulic pressure probably, but you will say that later. But let's move into, so as your job is specialist machine learning, and our podcast is all about industrial AI, machine learning. What exactly does Harvey, what exactly do you do in this area?
Yeah, so I think machine learning is quite an interesting topic for our products because, of course, we want to provide better products to our customers, especially with a focus on efficiency, so higher energy efficiency of the hydraulic systems. And also we want to provide a greater flexibility, especially nowadays where even these big machines we talked about get electrified. So you change from a diesel to an electric drive, for example, and then it's really important to, for example, be more energy efficient because you need to save space in the battery. And here, especially on the control side, like by controlling our valves correctly, you can have a great impact on the overall system performance, for example, energy consumption. At the moment, it's like this, that you might have, for example, many mechanical controllers in your system still today, or you have electronic controllers to actuate the electronical valves, but they are tuned suboptimally, nicely speaking. And why is this so? This is, I think, due to the nature of hydraulic systems, which are highly nonlinear systems. So you deal with effects like friction in the cylinder and in the valve, magnet hysteresis, turbulent flows, and so on and so on. And moreover, you need to be aware of different working conditions, perhaps due to temperature changes or oil degradation or even worn down components. So imagine, for example, you build a machine in the summer, tune your controllers in the summer, and then use the machine in the Canadian winter. You see that then perhaps your working conditions are totally different, your controller is not ideal anymore, and so on. And very often those effects, they are not modeled, or at least not completely modeled beforehand. Because, I think it's hard to describe all these effects physically, mathematically, and then also to have measurements for all these components and for all these effects that influence your system. So you don't really get perfect or very good simulations for any of our use cases because they are so many. And even if you get good enough simulations, you don't stop because nonlinear control here is a very own world, very mathematical, and you need a lot of in-depth knowledge because you have nowadays, for example, a linear controller, PID controller, which is pretty much standard in industry, but you cannot expect a simple linear controller to perform great in any given working point at any given time. You need at least have, for example, some gain scheduling. So you change your PI and D parameter over time, over working points, and so on. But with these many black boxes that I already explained, the design is quite challenging. And this is where I and we at HW think that machine learning comes into play and can really create additional value.
Okay, that's exactly my expectation. And we're going to be going into a bit more detail later. Hydraulics, yeah, very interesting. I studied, but not longer than a year, I think, civil engineering in the Netherlands, in Delft. But my topic was water, civil engineering, still hydraulics, which is probably still very similar. And in your case, it's, I don't know, what's in there hydraulically? Oil, some kind of oil pressure, or what is in there?
Yeah, it's basically some hydraulic oil.
Right. Very good. Okay. Moving into exactly the topic of where machine learning then may be able to help you. Let's talk, share with us as much as you can, and maybe start with one of your research projects, AI Valve. What is it about? Who's involved? And, have you been able to reach some first conclusions?
Yeah, so we are having a research project right now. It's called AI Valve, as you already mentioned. Yeah, what is it about? Here we mainly focus on investigating control approaches that are machine learning powered. So we could use, for example, the sensor and time series data that we get from a machine, from a hydraulic system, to identify the dynamics and also to get proper controllers for these identified dynamics. I think a very big constraint that should be mentioned here is that we usually don't have any sensor information or any sensor that we wish to have in our systems. So, for example, the volumetric flow. So, how much oil is in your system and goes through the system. This is usually quite expensive to measure, so you pay more than 1,000 euros perhaps for a sensor. The sensors are quite big and they are also not very robust. So you usually don't find these sensors in hydraulic machinery, especially not in mobile applications, if there isn't any very good reasons, for example, a safety issue.
Yeah, I understand. The good reason may be CO2 reduction in the next, 5 to 10 years, where the complete world needs to reduce, or I don't know.
Yeah, perhaps. But at the moment, we cannot expect to know, for example, the volume flows in our system. And often, I think you only have some pressures that you're measuring because pressure sensors are quite robust. They are also not that expensive. You know the electric currents that are applied to your valves. And perhaps, for example, the position of a cylinder, but also only if it's necessary for the application. And so you need to work with this very reduced information or with this very reduced set of information. And I think this is the great challenge for us to use this reduced information to get all the necessary information about system dynamics, to learn those system dynamics with neural nets, for example, and then to build proper nonlinear controllers on top of these trained neural networks. So who are we working with here? To overcome these challenges, we work with some great people from the Technical University of Munich, namely with the chairs of Automation and Information System from Professor Vogelhäuser and with the chair of Control Theory from Professor Lohmann. And yeah, with them we are combining our domain knowledge from hydraulics with their knowledge in control theory, in AI, automation, and also software design. Because when you want to sell like a machine learning product, you also need a good software design to run it on a PLC, for example. And yeah, with them, we are developing this concept for a machine learning powered valve that can use these reduced data streams for intelligent control. And I would say it's a tough challenge for us. But at the moment, I would say we are on a good path and on a good way and have some great ideas to achieve our goals and to provide a good concept.
Sorry, as I just interrupted you right there. I've been working with Professor Vogelhäuser, must have been 10, 15 years ago. I think it was OPCUA at the time. Is that just on a complete side note? Is that something you as a company are looking into as well, providing your hydraulic systems or machines at OPCUA? Or?
Yes, I think OPCUA is a topic for our colleagues, for example, in the production, but I am not an expert in this.
No, it's okay. Just on a specific now, assuming, and you say you feel you are on a good road, that you're going to be able to, to work with machine learning, getting a better insight. Now, is that going to be enough to kind of allow for future new machine learning based business models?
Of course, I think so. At some point, when we overcome like our research phase, we want to sell a product. And we always ask ourselves the question whether like these approaches that we're now having match completely to our current business model. Because at the moment, I mean, we're selling a valve. Perhaps you have some service agreement, but machine learning system is completely different because it lives from updates, from learning processes throughout the lifetime of your component. Perhaps we could also identify like how the system behavior changes over time and might be able to detect degradation of components, like for example from valves. And this would also be a nice, interesting information for customers so they can plan their maintenance cycles and hopefully save money through this. But yeah, I mean, in the end, it's always that we want to solve some pain points of our customers, and AI or machine learning is just one of many tools to solve it. So of course we need to develop our business models further, but always in a way that they are customer centric, that we see that we sell an hydraulic component. And so they will, in my opinion, be not necessarily very AI centric. So AI comes with it, but it's not like the main point of our business.
Right. Now you are a hydraulics component provider, right? So to your customers producing, for example, let's stay with the example of the excavator. So what I could imagine is that the excavator company is interested in, let's compare it with, Trump laser cutting. So they're moving to pay per part. So rather than selling machines, they make a contract and the customer wants to produce a number of, let's say, whatever, 100,000, iron parts. So maybe your customer is interested in selling to their customer a number of, cubic meters of sand. I don't know, but maybe that goes too far for the moment. I would completely agree with the sequence. You're first diving into what can you do with machine learning, what can you provide in addition to what you have been providing as a company, and then maybe at some point in time, on top of that, you or your colleagues can think about if there's some new business model based on top of that possible. Maybe move to another. You've written a paper for the International Fluid Power Conference that was in Dresden, I understand. It was about an application of machine learning to improve the performance of a pressure-controlled system. Can you please share with our listeners what is that about? Any findings, results, any conclusions that you arrive at?
Yeah, of course. Yeah, I think the title might be a bit bulky, but it's, in my opinion, a very good reflection from where we started our journey in machine learning. So we ask ourselves the question at the very beginning whether it's possible to apply machine learning to an hydraulic system and to get a better control performance as when you have an expert-tuned PID controller. Because, as I said already, PID controllers are pretty standard, and so it's more or less the benchmark for us, or we set it as our benchmark. Yeah, then we thought about, okay, how can we realize such a system? And we chose the deep deterministic policy gradient algorithm, the DDPG, which is known from Lillicrap's famous continuous control with deep reinforcement learning paper, where they solved like a bunch of widely known problems like card pole and pendulum and so on. So you can imagine it's a reinforcement learning algorithm we used here, and adapted the algorithm such that we fed pressure information from our system into it and also the electric current. And the RL agent tried to predict new values for our PID controller. And so the PID controller was able to adapt to changing working points throughout like the whole operating processes. And to benchmark this, I think we took a quite easy hydraulic system just to showcase. It contained 2 valves and a hydromotor, and we wanted to control a certain pressure level inside the system, while we applied unknown disturbances to the hydromotor. So we applied torques on the hydromotor. And the training happened in a quite simple simulation, which does not fully cover all effects that you have in reality. So just to name an example, we assume to have a perfect pump for the system, but of course, in reality, the supply is never perfect. And after the training phase, after the simulative training phase, we then applied the agent to a real test bench in our testing department. And yeah, we've seen that it performed quite well. It outperformed the expert-tuned PID controller, even though that the simulation was not perfect. And I think that was quite like an interesting outcome. Though, to be honest, we never trained the reinforcement learning agent on the real test bench, because we've seen in the simulation that it would require data from more than 24 hours of operating time, and this doesn't make sense energy-wise, but it also wouldn't be good for the hardware, because like when you have reinforcement learning, you have the exploration phase where the algorithm explores also like system boundaries and all that stuff, and that could harm the hardware. So we didn't do this. But I think overall we can say that these findings, they were so important for us, and that's why we wrote the paper about it, because we learned so much about like how to design a machine learning application for our purpose. And we learned, what are the points that we really have to consider when we do such things.
Yeah, please share later on the link to that paper, and I'll come to that later when we talk about the reinforcement learning as well. So there's 2 topics that I want to go into a bit more deeper. One is, you mentioned simulations. I want to talk about, let's say, the inter-exchange between, I call it more like forward-thinking simulation. Maybe you recognize that on one hand, and on the other hand, maybe it's oftentimes the backwards-looking machine learning, although that may not be the case with the reinforcement learning, but we'll come to that. And the second one is more of a hypothesis that I have. Whenever we, include, embed machine learning into automation systems, that we still always are going to have to need more like a rule-based system around it. Let's start with the first one. And it was a topic, as I mentioned, came up last week during the 2-day training as well. There was a lot of discussion about, engineers sitting there, and they have been trained as maybe very likely. You tell us you have been as well as a student. It was maybe typically, MassWorks simulation software. There's similar software from Siemens, from a couple of other companies. So it is this what I call forward-looking simulation. And then since a couple of years, and that's why we sit here, that's why we talk here, comes machine learning. Typically algorithms looking into data and trying to find patterns. So they are two, can I say, completely different approaches. It's almost like, my feeling is one is forward looking, the other one is almost like not backwards looking, but algorithms looking inside. Can you follow what I'm getting at? And can you confirm that that is a topic that is part of your research as well? And how do you deal with it?
Yeah, of course. I think you're totally right. And this is a discussion we also have sometimes. And I would say it like this. When we apply machine learning, for example, to our problems where we have time series and sensor data, we try not to, of course, we try to learn from the past, but we also try to extract the dynamics that are that define the ground of this process, and we try to build this process so we can use it as kind of a simulation. And I think also when you create some like forward looking simulation, I mean, what are you doing? You perhaps know the physical process that you want to describe, but when you want really a simulation that matches, for example, to a specific valve or a specific type of motor or so on, then you take measurement data, you are looking for effects and patterns in the measurement data, and then you try to adapt your simulation to the measurement data so that it's matching somehow. So I think with machine learning, we try to more or less automate this process. Of course, that's not I don't want to say that it's not good to have simulations, because when you really when you really know your physical process well, it's really good, and it gives you really more advantages for your future developments. But sometimes you just cannot describe the physics, or you don't have the measurements or the sensory information to get every information that you need to extract the dynamics. And there, I think machine learning can help. And when you do it right, then it can be also like a forward-looking process here.
I also can imagine, I'm not sure you have experience there, that it's kind of a psychological topic, for 1 or 2 generations. And I believe you said, including yourself, people, young people have been using simulation in their university environment and started working, and they came into an environment where colleagues had been working already 10, 20, 30 years doing the same thing, as you say, on the basis of physical knowledge, knowing as good as we know as engineers how the world works, right? We never know 100%. I guess we do it as good as we can by means of formulas, and then simulate as good as we can. Then comes machine learning as a new, let's say, not new as such, but since algorithms and computing power have come together in a way that we can now more easily apply it. And then maybe guys, women like yourself come in and show a different way of doing things. I want to refer quickly to Sepp Hochreiter a couple of weeks ago, and he said he was referring to hydrology, maybe very similar, but more like, as far as civil engineering, water and earth and rain and climate. And he said, the people in his team, they had been applying the machine learning, and it came up with models that was so powerful, relating to what hydraulic engineers have been doing for 50 years. So, long story. Question is, do colleagues that have not been using machine learning, maybe they worked 30, 40, 50 years for simulation. Are they open? Is it difficult to, work with them to convince him that machine learning can provide additional information and value?
I would say sometimes yes and sometimes no. It depends on the colleague. And I think it's also a thing how you talk with the people. So you shouldn't go to someone and say, hey, now I have machine learning and now I can do everything better that you were doing. But my experience is when you explain what the advantages of this tool machine learning are, then the people become open-minded.
Very good. More and more, I must say that I spend in trainings, in discussions, in moderating many, many more times this exact topic of the very, very important necessity to involve the people around you, and not only to involve the people that maybe are, I don't know, standing at the production line, or in your case, work with hydraulic components or systems, but also the engineers. It's so awfully important. Maybe more and more the technology seems to be working. But if we don't take the people around us hand in hand with us, then many times still at the end it doesn't work because second, and maybe we bring everything together a little bit more later on, but the second one is my hypothesis. So it's still in this combination of, as I said, so designing automated systems, embedding in today and in the future more and more, let's say, machine learning based systems with some kind of statistical basis. My hypothesis that always, also in as far future as we can normally see, that always on the outside of the system, let's say where the rubber hits the road, we're always going to need a rules-based system to control these systems. So we're going to be using more and more as embedded parts the additional knowledge of machine learning. But at the end, where the system, the excavator decides, to move up or down or left or right, it always has to be a rules-based system. Do you buy that hypothesis from me, or?
Yes, I think this will be the near future. In my point of view, what's really important is that we shouldn't learn, or we shouldn't have a learning or training phase when a machine is running. We need have special maintenance modes for that, and we need really to ensure that we only apply, in our case, controllers to systems that achieve a certain level of stability and robustness, so that nobody needs to worry about safety issues. And of course, when we detect some abnormality in our system, in our control performance, then we should have very basic, for example, stabilizing controller that is perhaps not energy efficient, not as performant, but avoids harm.
Right. So some kind of sanity check values, whatever they are, that make sure you're going to have like a rules-based degradation of bringing it back to normal. But yeah, the thing I'm not sure I understand. You say you're not thinking of learning. I think you mean the machine learning training data when the machine is running. Not sure I understand that clearly.
So okay, I meant that we won't train our, for example, a neural network when you are really in the field and I don't know, your excavator really does productive work with a person sitting inside. And I think we should really use a special maintenance mode for that, where we can ensure that no people are around that can be harmed and so on. Because, you never know what happens here and what the machine does.
Yeah, I think I understand you. But you can always, of course, track and gather the data, during while the person is working, and take the data off site and then train the model, right?
Yes, that's a point. If you have the data storage capabilities in your machine, then this is possible.
Yeah. I just recall, just coincidence, another Trump, in this case, application they mentioned just some time ago on the podcast, where they had some knowledge, some assumption, some additional functionality which they did not, yet make available to the customer, but it was included in the model on the machine, and by means of like a camera looking at what was going to happen, they had their model predicting something is going to happen, and they had a camera which was then confirming that something would happen or not. So that almost like a confirmation. You mentioned time series data, which is that's what we typically and very often use in our automated systems. What role do time series data play in your paper, and in general, as far as machine learning, hydraulics goes? Can you tell us about the state of the art of machine learning in time series?
Yeah, of course. I mean, when we talk about sensory data, I think it usually implies that we have some sort of time series data here, because we have measurement value, we have measurement time, and the pairs over time give us time series. And I think everybody knows like these very common time series processes, like the weather data, stock market data, and so on. And what we see here, that people try to estimate further developments, for example, for the weather, for the stock market, by using this time series data, this historic data. And I mean, sometimes it works quite well in case of the weather, for example, sometimes not that good in case of the stock market. Otherwise, we all would be rich by now. At least machine learning engineers would be.
Some of us are maybe, but they don't tell us how they became rich.
Perhaps, yeah. And I mean, all these processes have in common, and also in common with our application, that they are highly nonlinear. And it's very hard to fully describe them by hand, even if you're a very good trained engineer. So perhaps you need some combination of models. For example, you combine your physical process that you know with a NARCS model that represents your unknowns. For example, hysteresis effects or friction. And in the end, when you use the time series data to extract dynamics information, you're left with somehow a regression problem. I think it comes always down to like you have some regression problem. And I mean, also in hydraulics, as I already said, we have pressure signals, electric current signals, and so on. And they relate to each other over time. And we use this time series data to not only predict our process, but also to design controllers on top of these identified models to influence our process in the future. And in my point of view, this is quite a heavy requirement when you have this closed control loop, because we need to build and identify really, really good models of our systems here in order to get stable controllers that do not do crazy stuff or even harm machines and people. I think when you've worked with control theory, control systems, you know that when you don't have a good model and you tune a controller with it, and then you go onto a machine, you get oscillations and all that stuff. And so we really need to come to a point where we can trust our models, but also we need to design controllers in a way that they are safe and robust, because we never ever will get like 100% perfect model, because time series data, I mean, it's not endless. We only have some measurement points, and they cannot possibly include every like working point and every condition.
Robustness is an important part of trustworthiness. I just recall I listened this morning, last night, to a podcast Robert did with a Kees Snoek professor in Amsterdam. It was one of the many topics they're looking at. And, trustworthiness is the big topic of the European AI Act. Let's see where we're going to be moving to there. Now, when we talk time series, correct me if I'm wrong, typically we would apply supervised or unsupervised, depending on what it is that we want to do. Now, you mentioned the third category, what I call the third category of reinforcement learning. And that, as far as I'm concerned, as I know, and you can tell me, typically used for, you just mentioned, designing. It's more like looking into the future, giving the algorithm, a couple of goals, spec maybe that you're looking for, and agents are going to help you to, for example, I don't know, design the new machine. So how do you use those different ones? And what I would say, looking back, looking at the time series from the past and try to put them into the future, i.e. predictive maintenance on one hand, and reinforcement, which I see as the most, let's say, creative of the machine learning approaches, as you may be using them in your company.
I agree that reinforcement learning is perhaps the most creative thing that you can do in machine learning, and I think it has the most potential for the future. But the problem with RL is always that it's quite data hungry, and learning through interaction is, at least when you go out in the real world onto heavy machines, sometimes quite a bad idea, because in the exploration phase, when anything can happen. So I would say at the moment, I don't see that we use RL algorithms outside in the field in hydraulic systems. Perhaps we might use it, as you said, for design purposes in the construction phase, but not for control. I think that was some outcome of our paper. But as you mentioned correctly, with our time series data, we are using supervised learning, or we're doing supervised learning. And we're doing the supervised learning part only on the system identification process, while we are using like classical nonlinear control approaches on top of our models. But if time goes on and new data comes in, we are improving our system. So we can fine-tune our model, and thus also our controller that gives us the action that we are taking improves. So you always have like supervised model improvement, and then you also get an improvement of your control and your control actions. And so perhaps if you want to do the stretch, you could also call this some sort of reinforcement learning. Because over time, when you're interacting more and more and getting more experience through time series data, then you're also getting better in what you're doing.
Right. The interest that you refer to reinforcement learning, maybe at the different stage, I don't know, as being data hungry, I had it almost like different in my brain. I mean, it's the different approach where, supervised, unsupervised, I have, little or a lot of data, but, algorithms look for patterns in that data, while reinforcement learning, is more like, I set up like a working space. I don't know if it could be your physics-based simulation, maybe, like, and agents look for the targets that you give the agents, right? So where does this data hungry come from, just from my understanding?
I think in our case, the data hungriness comes really from the many different working conditions and working points that we are talking about. And I think at one point or another, we need to represent them, perhaps in a simulation, but then we need a lot of measurement data to do our simulation correct. Or we say, okay, we don't simulate this, but we need to have these conditions when we are using the RL algorithm and train it then. And either ways, you need a lot of data to really get a good output.
Right. Don't forget, I'll remind you later to share with me the link of the deep reinforcement learning, just for listeners to know as well who might want to be reading that. So, we could be talking for hours, I feel, but we can't. So moving towards the end, tell us maybe a little bit, as far as you can, your machine learning environment. You're using any specific platform, internal, external, any language, any specific tools that you can share with us?
Yeah, I think it won't be a surprise to your listeners, but in order to build fast prototypes, we are using Python in combination with NumPy, TensorFlow, PyTorch, and so on, whatever matches best. But I think the interesting part is when we want to get real, like to test our models on real hardware, on hydraulics, then we have to translate our algorithms to C code, because otherwise, it wouldn't run on the established PLCs. at least the PLCs that we use in hydraulics. And I think that's quite interesting part. So to break down everything that your toolboxes do in Python, very automated, then into very efficient C code.
Are PLC providers going to give you the option to run Python code in the future? Have you ever discussed that? Are you aware of that?
It might be possible, yes, but I don't see it for the near future, but perhaps in the long run.
Is that a huge step, this translation Python to C, or
yes,
like takes a couple of days, couple of weeks, or
it depends on what you're doing, but I think it can take a couple of weeks to do this, at least when you're doing it for the first time. But then when you get your routines and you can reuse a lot of code later on. So
good. Maybe you're a team. Are you alone, so to say? Is there any other people with you doing machine learning, or more colleagues doing the simulation? Maybe you're looking for colleagues to join. If so, what capabilities should they bring to the team?
Yeah, so one thing, of course, we at HW don't have an AI or machine learning team. So I'm just normal part of our R&D hydraulic components department. And we see this development of AI solutions also as a very interdisciplinary task. So in our project teams, we are like highly diverse in terms of our background. We have people that come really from hydraulics, from hydraulic constructions. We have people from control, and of course, very important, people from simulation and testing. So to validate our systems. And yeah, of course, I bring the knowledge about machine learning and about control theory. And it's always a bit funny because it's quite a big challenge to bring all these domains together and to speak the same language. But I think it's also very nice because we have an opportunity to really shape the direction in which the company is going, and that's really cool. Yeah, I think over the years also, I mean, I'm the only machine learning engineer to answer this question. A lot of people around me, like my boss and so on, they really developed a quite good understanding about machine learning and AI. So they are really good sparring partners now, which is very great.
Very good. Another important confirmation of humans working together, and humans, engineers, typically, as most of our listeners probably are. As long as we keep an open mind, then we can and we should be working from all these different disciplines, see what works best, and how all these disciplines bring something to the table. So, coming to a close, where do you see then, AI, machine learning in hydraulics? Where do you see it today? In Germany, Europe, referring to you're a global company, maybe things that you hear from your colleagues in US, China, Asia. And how is it going to change exactly the world of hydraulics in the next 5-10 years?
I think, as we already made clear, hopefully, in our discussion, that machine learning powered products are also the future of hydraulics. But I'm not sure whether everything will be sold under an AI label. Because I think that sometimes you will get a product and you don't even know that there's machine learning inside, just because the machine learning part happened like in the construction or design phase or in the production. But I think there are so many great opportunities to use these technologies in any department of an hydraulic company. And of course, I would say in the hydraulic sector, many big players are coming from Europe and the US, and we will see a lot of innovations coming from here. But also we need to act fast, especially in Germany, because the others are not sleeping, and especially China might push the development extremely in the near future. We see this in other applications as well. So I think China will really well perform here. And so I also want to refer to Sepp Hochreiter. He's right when he says, vermassel das nicht. So don't mess it up.
Don't mess it up.
Because we need really use our advantage and our advance that we have at the moment and combine it with this new technologies like machine learning to stay on top. And I mean, it's a tough challenge, but I think now the decision makers in the industry are getting it more and more. And I think we're heading in, let's say, in the right direction. And hopefully it's fast enough.
Fabian, thank you very much. That's a great close with Sepp Hochreiter. Don't mess it up. That's kind of how Robert and I started this podcast almost 4 years ago, I believe. For those of you listeners, that is in German. If you're interested, we might be able to provide you with a translation version of that. And in as far, your marketing, business development colleagues are going to decide to sell your products in the future with a big AI label embedded or not. I think it's on one side, it's a marketing thing. On the other side, we need to wait for the European Commission. They're in the middle of deciding what is AI, what the definition of what is AI, etc. So it may be that, maybe not your components, but at least the machines, as an example, the excavator machines, that they're going to have some kind of logo that's going to show the users that they have been tested as trustworthy AI. Great, Fabian. Thank you. It was very interesting talking to you, and especially as you and listeners could tell, my strong interest in the exactly the combination of your topic, of the combination of control and machine learning. So, any listener that maybe has a question for you, wants to do something with you, how really can get in touch with you, best on LinkedIn, Fabian Kreutmeier, beautiful, explicit Bavarian name, Fabian, Fabian, and Kreutmeier is Kreutmayr, Kreutmeier. Otherwise, if you, dear listeners, have any questions, comments, please send a short email to robert@aipod.de or peter@aipod.de. I'm very happy you stayed with us so far. Looking forward to have you with us again this time. And Fabian, thank you very much again for your time.
Thank you.